good morning, good afternoon, and good night to everybody. Today, this is the 6th class in Physics 1 part. Today's topic is fluid dynamics, especially the viscosity. We'll discuss here actually what is viscosity, coefficient of viscosity, and Poiseuille's equation, determination of the coefficient of viscosity by different methods, especially Stoke's method, and Bernoulli's theorem and its application. This is very important theorem in fluid dynamics. So, and Venturimeter, Torricelli's theorem, some real life examples. So, welcome to my class, and I hope you'll enjoy everybody. First of all, what is fluid? A fluid is a substance which deforms continuously or flows when subjected to shearing force. This is the shearing. Shearing means you must know about freedom or pressure. In fact, if a shear stress is acting on a fluid, it will flow. And if a fluid is at rest, there is no shear stress acting on it. So depending on shearing stress, there are two types of fluid. One is if fluid flow, then shear stress and it will be yes, and fluid rest, shearing stress will be absent. So according to the shearing stress in moving fluid, we can divide it into two categories. So if fluid is in a motion, shearing stress are developed if the particles of the fluid move relative to each other, and on the other hand, the velocity of the fluid is the same at every point. That means there will be no flow of the fluid. So fixed surface and new particle position, shear force, and moving force. So fluid particles will move due to shearing stress. So there are different difference between liquid and gases, and we have discussed in our previous lecture, lecture 5. So suppose liquid difficult to express and when regarded as incompressible. Okay, so easily to compress, changes of volume is large and cannot normally be neglected and are relative to temperature. So, and on the other hand, there are two types of fluid. One is Newtonian fluid and another is non-Newtonian fluid. If the fluid obey the Newton's law of viscosity, and it's called Newtonian fluid. So Newton's laws of viscosity is given by tau equals to mu du by dy, where tau is the shearing stress and mu is the viscosity of fluid and dy is the rate of shearing. So for example, air, water, oil, gasoline, alcohol, kerosene, benzene, glycerin, etc. So, and non-Newtonian fluids which doesn't obey the Newton's law of viscosity. So in that case, we get non-Newtonian fluids. So this is the example for non-Newtonian fluids. And this is the graphical representation for different fluids. There are different kinds of units we have to use. And this is the quantity and SI units. And this is the derived units we have to use. So depending on different fluids, there are different branches for study. Suppose fluid mechanics and fluid statics, fluid kinematics, and fluid dynamics. Actually, we are concentrating on fluid dynamics, but we'll discuss about the different kinds of terms for the fluid. So fluid mechanics equals to it is the branch of science which deals with the behavior of fluid at rest as well as in motion. So fluid static and it will study of the fluid at rest, and fluid kinematic is study of the fluid in motion where pressure forces are not considered. But in fluid dynamics, the study of fluids in motion where pressure forces are considered. So you have to remember this. And what is the actually density? Density or mass density of a fluid are defined as the ratio of the mass of fluid in volume. That means mass per volume is called the density, and a specific weight or a specific weight density. Specific weight of a fluid is the ratio between the weights of a fluid of its volume. Similar to W equals to rho G rho. And a specific volume and a specific gravity also can be defined by this. So a specific volume equals to volume of the fluid divided by mass of the fluid. So volume of the fluid is 1 and mass of the fluid per kg equals to rho, which is the density. So specific gravity also can be defined by the ratio. And the standard fluid for liquid is water and for gas is air. You have to remember this. Standard fluid will be for liquid is water and for gases will be air. So what is the actually viscosity? Now, viscosity is defined as the property of a fluid which offers resistance to the movement of one layer of fluid over another adjacent layer of fluid. So you must know in every fluid has a layer. So an internal, another is external layer. So the viscosity is the actually is kind of property of a fluid which offers the resistance to the movement of one layer of fluid over another adjacent layer. So this is the one kind of property of fluid. Consider two layers of fluid a distance dy apart from the velocity u, so u plus du. The viscosity together, relative viscosity causes shear stressing. So acting between fluid layers, shear stress is property proportional to the rate of change of velocity with respect to y. So this is the actually formula for viscosity. Now mu equals to coefficient of dynamics viscosity and mu equals to tau divided by du dy, where viscosity is also defined as the shearing stress required to produce unit rate of shearing strain. SI units will be Newton second per meter square, and in CGS dyne second per centimeter square. It's called also Poiseuille. Now Newton's law of viscosity, it states that the shear stress tau of a fluid element layer is directly proportional to the rate of shear strain. This is actually Newton's law of viscosity. And kinematic viscosity. Kinematic viscosity is defined as the ratio between the dynamic viscosity and density of fluid. So this CGS units is Stokes. Now types of fluid: ideal fluid, rare fluid, Newtonian fluid, non-Newtonian fluid, and this the graphical depiction for different fluids due to the shearing stress. Now, effects of temperature on viscosity, you must know, we have discussed in our previous lecture in surface tension. So, viscosity, a liquid may be considered to be consisting of molecular layers arranged one over another. So when shearing force is applied to a liquid, it flows. However, the forces of friction between the layers offer resistance to this flow. So the viscosity of a liquid is a measure of its frictional resistance. Let us examine a liquid flowing on a glass surface. Suppose this is the molecule layers and this is the moving plane, and this the velocity will be v and velocity profile. And there is no shearing. This is why velocity will be 0 for that. Okay. So flow of liquid in a glass surface. Now the area change in velocity v plus dv. So a little change in length dx, and the initial velocity will be v. So in that case, we can define the coefficient of viscosity. So the shearing force will be proportional to the surface area and the rate of velocity. Okay, so this can be written as F equals to eta a dv dx. Here eta equals to actually coefficient of viscosity, and units of coefficient of viscosity will be this, we can derive this. One Poiseuille equals to 1 gram per centimeter per second. That means 0.1 kilogram per meter per second. This is the unit of. Now the streamline motion and rate of flow. Actually, this is the this is a tube in which fluid is flowing. Consider a liquid flowing through a pipeline. Let B be the velocity of flow and I is the area or cross section of the pipe. So volume of liquid flowing per unit time can be calculated. This equals to L multiply A divided by T. So this equals to V multiply T multiply A divided by T. And this TT will be cancelled. So B A. So AB, area of cross section multiply velocity of flow. So the flow of liquid through a pipeline is said to be the steady or streamline if at any given point the velocity of the particle is constant. It means that all the particles of the liquid passing across the point have the same velocity. So in this case, the streamline motion at any instant, the tangent to the curve gives the direction of the flowing flow. The streamline may be straight or curved. The condition for a stream, the line motion depends on the velocity of the fluid flow. So if the velocity does not exceed the certain limit value called the critical velocity. You have to remember, this is the definition of critical velocity. Flow is said to be streamlined if the velocity of flow is higher than the critical velocity and motion is said to be turbulent. For laminar flow, Reynolds number R should be less than 2000. So according to the Reynolds, the critical velocity of liquid is given by capital R eta divided by PD, where capital R is the Reynolds number, eta is the coefficient of viscosity, and rho is the density, and capital D is the diameter of the tube. Actually, using this application from different countries, oil, gas can be supplied to another countries by a huge pipeline. Okay, for example, Russia giving their oil and gases with a huge and long pipeline. They are supplying these fluids with all over the Asia and Europe. So, for example, water flows through a horizontal pipeline of a varying cross section of the rate of 0.2 meter cube per second. Calculate the velocity of water at the point where the area of the cross section of the pipe is this. Rate of flow is AB, where B is the rate of flow divided by A. Here the rate of flow will be 0.2, A equals to 0.02, and B equals to this. So now, what is continuity equation? Consider a horizontal pipe. A liquid is flowing through a pipe. The liquid is assumed to be the streamline motion. And suppose area of the cross section at A part is A1, area of the cross section at B part will be A2. As there is no accumulation of the liquid at any point, the amount of liquid flowing per second is the same at all the cross section of the tube. So amount of the liquid flowing per second will be A1, B1, and amount of liquid flow per second will be B equals to A2, B2. Actually, this flow will be equal. This equation is called a continuity equation. In general, AB equals to constant. Energy of liquid in motion, different kinetic energy, you must know kinetic energy equals to half mv square. But for unit mass, this will be half b square. And potential energy, you must know mgs. But for unit mass, this will be m equals to 1, mass equals to 1 kilogram. This is why z is. So, and pressure will be Pb by m per unit mass. But for unit mass, this will be P by m. Now, we'll Okay, now we'll measure the actually viscosity. Whenever a liquid flows on a horizontal surface, the velocity of different layers of the liquid parallel to the fixed surface are different and increase with the distance from the fixed surface. If the motion of the liquid is streamlined, the layer of the liquid is in contact with the fixed surface is stationary. The velocity of any layer increases with the distance from the fixed layer. If any two layers are considered, the upper layer tends to accelerate the motion of the layer. Suppose this is the steady and this is u plus du and this is the u velocity. So using this property by virtue of its which liquid opposes the relative motion between the different layers is called the viscosity or internal friction. Generally, thin liquids like alcohol, water, spirit, etc. are less viscous, whereas thick liquids like coal, tar, castor oil, glycerin, etc. are more viscous. So according to the Newton's law of viscosity, the backward tangential force F on any layer is dependent. So force is proportional to the area of the layer. And secondly, this force will be proportional to the velocity gradient at the layer. That means du by dx. So the force is proportional to the A multiplied du dx. And therefore F equals to eta A du dx. Actually, eta is called the coefficient of viscosity of the fluid, and du divided by dx is called the velocity gradient or change of velocity with the distance or rate of change of velocity of liquid with respect to distance. The negative sign shows that the force is acting opposite to the direction of velocity. We have to remember this. And if A equals to 1 area and rate is 1, then we get F equals to minus eta. In that case, we can define coefficient of viscosity as the tangential force required to maintain a unit velocity gradient between two layers of area with what? 1 unit. That means units will be what? If I is equal to 1 square meter and the rate is 1 and force will be 1 time. In that case, eta can be defined by Poiseuille. So what is Poiseuille? This Poiseuille is the unit of actually coefficient of viscosity. So the coefficient of viscosity of a liquid is 1 Poiseuille if force of 1 dyne is required to maintain a velocity gradient of 1 unit between two layers of unit area. That means 1 square centimeter. Now dimension can be found. Eta equals to dimension of F, dimension of area, dimension of gradient velocity. So dimension will be this. Now Stoke's law. Suppose the resultant force acting on a ball becomes 0 and it moves with a constant velocity is called terminal velocity. So resistance force F acting on the ball depends on the radius of the ball R, the terminal velocity B, and the coefficient of viscosity. Okay, not actually velocity. This is the mistake, and this will be the viscosity. Now expressing the dimension, F equals to what? K R to the power A, B to the power B, E to the power C. Actually, this is ABC are unknown for us, but by using dimensions of unit, we are deriving the Stoke's law. Now F dimension equal to ml per t square. This is the force unit. So equating on both sides, power of m, power of L, and power of capital T. So equating the powers, we get A equals to 1 and B equals to 1, C equals to 1. Substituting these values, F equals to K R eta B. Okay, K R eta B. But according to the Newton's, according to the Stokes, K equals to 6 pi is a constant. So 6 pi F equals to will be what? 6 pi eta RB. Coefficient of viscosity of a liquid can be determined by Stokes formula. Now, suppose radius of ball will be R, terminal velocity B, coefficient of viscosity eta, density of the ball rho, density of the liquid sigma. Net weight of the ball will be 4 by 3 pi R cube. This is the volume. Net weight, mass. So rho minus sigma into C. So upward force due to the viscosity 6 pi R eta B. Actually, this equation number 3 and 2 are equation number 3 and 2 are equal. So we can easily get B equals to this and eta equals to this one. Hence, eta can be determined. So by Stokes' law is applicable to determine the coefficient of viscosity at highly viscous liquids. Now we can give an example. Find the limiting velocity of a raindrop. Assume diameter is 10 to the minus 3 meter. Density of air will be this. Coefficient of viscosity of air will be this, and density of water is 1000. Everybody is known. So according to the Stokes law, 6 pi r eta b equals to this one. So b equals to this, and b equals to, you can write, actually taking rho common, we get this. Now putting the values, we get easily the r equals to radius will be 30.04 meter. B equals to velocity will be meter per second. Now similarly, another example, two equal drops of water, each of radius r, are falling through air with a steady velocity v. If the two drops collapse to form a bigger drop, energy released and fluid the new velocity of all. Now using similar equation, bigger drop, radius of bigger drop will be capital R equals to this. Decrease the surface area, so we get easily energy released is this. Again, let the velocity of bigger drop of be capital B. So in that case, for a small drop, weight equals to mg equals to this. Then mg means what? Actually force. So for the bigger drop, twice mg, because twice 6 pi r eta b. Dividing, we get this. Now Poiseuille's method for coefficient of viscosity. Rate of flow of liquid through a capillary tube depends upon the length of the capillary tube, radius of the capillary tube, and pressure difference between two ends of the capillary tube. So coefficient of viscosity of the liquid. It is also assumed that the flow of liquid is a streamline and the liquid is constant with the walls of the tube is at rest. And the tube is kept horizontal. And fourthly, the pressure at any gives cross section is constant, and there is no radial flow of liquid. This is the actually length L, and this is the tube. So this is the actually circular part of a tube, and this is the center X, and this radius will be R. And after within X radius, we can draw another circle. So consider a liquid flowing in a capillary tube of AB. Actually, capillary tube of AB. So length L and radius R. The layer at the entire of the tube has maximum velocity, and the velocity decreases from the axis to the walls of the tube. Let a layer be at distance x from the axis. The other layer is at a distance x plus dx from the axis. The tangential force acting in the opposite direction to the direction of the flow is given by F equals to minus eta A du dx. Actually, this is the given by Newton's law of viscosity. Here, capital I is equals to twice pi xl. Okay, F equals to this. Equation number 1. The force at the end A of the tube will be F equals to P pi r square. That means whole area. Whole area. Where is the difference in pressure between the two ends of the capillary tube? Now, these two forces will be same. So equating equation 1 and 2, we get the gradient velocity will be equals to minus bx divided by 2 eta L. So d equals to this. Now integrating with respect to u and x, integrating on both sides, we get du actually px square divided by 4 eta L. X will be 1 plus 1 divided by 1 plus 1. This is why half and half will be 1 by 4 eta L. So d this is equals to u equals to this, and where k is the integral constant. Now when x equals to r radius and u equals to what? Velocity will be 0. In that case, k equals to, we get p r square 4 pi L, and u equals to what will be? U equals to this. U equals to what? This is actually u, not du. This equals to what? U. This not du. So u equals to this. U equals to minus this plus putting the value of k. This is the value of k. Just subtracting. Now equation 4. Equation 4 gives the velocity of liquid for a layer of radius x. Now volume of the liquid between two layers per second equals to dV, or change in volume. So change in volume equals to actually circumference and distance in change into U. That means dV equals to just putting the value of U from here. So rate of flow of liquid through the whole tube is given by just integrating on both sides. So integrating on both sides. And we have to integrate 0 to radius R. Okay. 0 to radius R. We have to integrate whole for the whole tube. So from the center to radius R. Now after integrating, we get B. dV integration what will be B, and this integration with respect to what? X. This is the constant. So R square X minus X cube. Now just integrating X integration X square by 2, and X cube means X to the power 4 by 4. So this is X actually here. This will be actually R cube by X square by 2, and this is the X cube by 2. Just putting upper limit and lower limit, we get. There is a mistake. This will be R square by 2, and this is by R4 by 4. We get this easily. Now it equals to this. In this experiment, a capillary tube AB is fixed as shown in the following figure. So, but pressure equals to H rho Z. The radius of the tube is measured with the help of traveling microscope. The difference in the levels of the manometer gives H. So from the equation 6 and eta can be calculated by using this capillary tube. Okay, this is the AB capillary tube. There is a correction on Poiseuille's equation. So the correction will be pressure, coefficient pressure P1 is given by P minus P dash. Kinetic energy given to the liquid per second, E dash equals to 0 to R half mu square. Just putting the value of U from previous equation, where you give X, and U equals to this one. Now E dash equals to, you can easily calculate the correction. So at the inlet end of the tube, the flow of the liquid is not streamlined for the some distance. Consequently, it equals to this. So this is the actually correction. There will be plus minus here. Now some application. Water flows through a horizontal capillary tube of 1 millimeter internal diameter and less 70 centimeter under pressure of a column of water 30 centimeter in height. Find the rate of flow of water through the capillary tube. This is the rate of flow. B equals to pi P R to the power 4 divided by 8 eta L. So pressure equals to 0.3 Newton per meter square. So R equals to 0.5 millimeter, L equals to 0.7 meter. It equals to this Poiseuille. This is the coefficient of viscosity, and B is what can be calculated. Okay. Similarly, we can discuss some application on gaseous liquid. So cylindrical vessels of radius 0.07 meter filled with water to a height of 0.5 meter. It has a capillary tube. This we can calculate the time in which the water level will fall to height of 0.25 meter. Now this is given, eta and z is given. That the rate of fall of height with the time will be dH by dt. Rate of flow of water B, area of cross section will be capital A. So B equals to minus A dH by dt. So B, but again we get this from the previous theorem of viscosity. So actually this this total area will be equal. So in that case, dt equals to this one. Now integrating on both sides, left hand side 0 to capital T and right hand side H1 to H2. This is the rise of liquid. Okay, rise of liquid from first height to second height. So With respect to a's, we can integrate 1 by x formula log x, so log n by n. So now just putting upper limit and lower limit, we get this. Just putting all the values, a equals to pi r square and it equals to, this is the coefficient of viscosity, and is the 0.1 meter. So putting all the values, we get the actually capital T value, stress, time, this is the time, 48.14 hours. Similarly, another example, cylindrical vessel of diameter. Here we have to find out the level, half the initial height. Till half the initial height is given, similar procedure, and height will be the h1 equals to, h2 equals to what will be? Half into h1. That means h1 divided by h2 equals to 2. Just putting all the values, we get this. This is another example. This is according to the Poiseuille's formula. Just putting the values on the chart. And this is also, this is the Newton's law of viscosity, and it is the coefficient of viscosity. A large bottle filled, same equation, just putting all the values. We get the ratio of the coefficient of viscosity. Similar example, using the Poiseuille's equation, and pressure equals to H rho Z. Total volume can be calculated. Same example. This is also another example. This is the Stoke's equation. Using the equation, you can calculate the coefficient of viscosity. And here also, calculate the pressure at M point. So in this part,
now we will discuss another important equation is or theorem. Bernoulli, this is called Bernoulli's equation. That means the energy per unit volume before equals to energy per unit volume after. For a pipeline, there will be velocity P1 and for pressure P1 and velocity P2 for pressure P2. So we can calculate the pressure energy plus kinetic energy per unit volume plus potential energy per unit volume will be constant for any fluid. So now we'll discuss about this theorem. This theorem, according to the name of Daniel Bernoulli. He's a great scientist and mathematician from a Bernoulli family. There are about 6 scientists from this family. We'll discuss about the application of Bernoulli's principle. This is the fluid moving in a tube. So pressure plus P and so here actually this is the Bernoulli equation, and this total volume will be constant. So if no change in height, then this will be constant. This is actually kinetic energy, and this is the total pressure. So this for the no change in height, potential energy will be 0. So this is the constant for this case. Now faster speed, this in this case faster speed, and this is the slower speed for the bigger tube, and for the smaller tube pressure will be high. This is why faster speed, and this is here slower speed of liquid. So more pressure here and there less pressure. So as the speed of a fluid increases, the pressure in the fluid decreases. We have to remember this. This is the mainly Bernoulli's principle. As the speed of a fluid increases, the pressure in the fluid decreases. So pressure is proportional to 1 by B. If the speed is increases, pressure will be decreases. So motion of fluid actually due to energy, and pressure in fluid also due to motion of fluid will be kinetic energy, and pressure of fluid will be potential energy. So we have to remember these two concepts. Now kinetic energy plus potential energy must be constant. So for this principle, if incompressible fluid density rho change in pressure, okay. So if the diameter becomes the 1/4 part of diameter, then it will be. This is the actual application of Bernoulli's equation in aeroplane and Bernoulli and flight. This is the Bernoulli principles is what allows bird and planes to fly. This is very real life example. So the secret behind the flight is under the wings. So air or wind giving pressure. So the faster air, less pressure, wing goes up, and air hits bottom of wing, bounces down, wings goes up. So airfoil, this is the on top greater air speed and less air pressure. On bottom, less air speed, the more air pressure. Okay. So for this reason, airplane flies speedily, and drag, that means more pressure, and thrust, give more thrust. So lift the airplane to the sky, and due to the and behind the gravity. So there are 4 parts. One, lifting the airplane against the gravity, because due to the drag or pressure, and give the thrust. So net force on wing will be like this: air or wind giving, and wings faster, more pressure up, so less pressure down. This is the application. So half a rho B2 square minus B1 square. This is the rho of air will be 1.29 kg per meter cube. So spoiler airfoil reserved, and greater air speed, less pressure. So less air speed, more pressure. Actually applying this principle, that means Bernoulli's principle, every airplane and flies faster. Net force equals to downwards. We can give this example also. Spoiler provides better traction and avoids lift. Wind over a roof. This is the proof. So atmosphere pressure equals to pressure on roof plus half rho B square. That means kinetic energy. Okay. This is the fast air speed, slow air speed, low pressure. And car ball also acting by using this principle: higher air pressure, flight path, and ball rotation. So lower air pressure. This is the no spin, but this will be spin because here pressure acting and tars also acting. So flow fast a golf ball and turbulent boundary layer, golf ball dimples, and winds over a mountain. Here 50 mile per hour speed and 25 mile per hour speed, but at the top 100 mile per hour because there is due to the more pressure. And shower curtain, this is also if you give the shower on a curtain, পর্দার উপর যদি আমরা পানি দিই ঝর্ণা থেকে, তখন এটার অ্যাপ্লিকেশনটা আমরা দেখতে পাবো। In speed of car, atomizer, as air passes at top of tube, the pressure decreases, fluid is drawn up the tube. So this is the application of Bernoulli. So for energy conservation, Bernoulli equation also can be written. Recall Euler equation, dp by rho plus b dv and z dz equals to 0. Also recall the force are neglected. Flow is inviscid. If one integrates Euler equation along streamline become 2 points. Just using integration, we get the actually Bernoulli equation. Here P1 by rho equals to flow of work. B1 square by 2 is kinetic energy. ZZ1 is potential energy. And this is the initial or before energy. And this is the last energy or final energy. And this equals to actually constant. So Bernoulli equation, flow of work. It is work required to move fluid across the contour volume boundaries. This is the actually consider a fluid element of a cross section area A and pressure P acting on a contour surface. So due to the work done per unit time will be rho, will be P at del x by T, and P by rho equals to this. That means P by rho equals to flow of work per unit mass. Actually, this is the Bernoulli equation. Okay. Now we will try to derive the Bernoulli's theorem. Now, according to the Bernoulli's theorem, the sum of the energies possessed by a flowing liquid at any point is constant, provided the flow is steady and non-turbulent. Consider the incompressible liquid like water in a pipeline. The motion of the liquid is streamlined. Let the pressure of the liquid at the cross-section A1, A2, B, P1, and P2. The area of the cross-section will be A1 equals to A1, and A2 will be A2. So the velocity flow of liquid A1 is V1 and A2 will be V2. In that case, with the work done per second on the liquid entering A1 first surface area, W1 will be P1 A1 V1. So for the first, this is the actually tube and liquid passing through it. So this is the first surface area A1 and second surface area A2. Here pressure P1 and velocity V1, and here pressure P2 and velocity V2. And this is the for calculating the potential energy, this height will be H1 and this height will be H2. So for the work done for the second by the liquid leaving A2 surface area, so work done will be P2 A2 B2. Net work done on the liquid will be W equals to W1 minus W2. In that case, just sum. But A2 B2 equals to A1 B1. This is the continuity equation we have derived in our previous slide. So this, by using continuity equation, W equals to what will be just P1 minus P2 A1 B1. This work done on the liquid contributes for the changes in kinetic energy and gravitational energy. So change in gravitational energy, what will be? E1 equals to rho z, A1 B1 P1 rho z H2 minus S1. Change in kinetic energy will be half m b square. This is actually mass per unit volume. So total work done will be E1 plus E2. In that case, this equals to this. So just putting the values we get this equals to this. This is the before and this is the after. So actually this is the constant b square by 2. This is the kinetic energy. This is the potential energy. This is the pressure. So this equation represents the Bernoulli's equation. Dividing equation 2 by z, we get this constant. Here b square by 2 z represent the velocity of head, and h represent the gravitational head, and p by rho 0 represent the pressure head. Special case, in case of horizontal pipe, a is the constant, b square by 2 plus p by rho equals to constant. So p plus half rho b square equals to constant, where p is called the static pressure and half rho b square is called the dynamic pressure. And this is alternate proof for this Bernoulli's equation. Just volume of the element will be this, mass of the liquid will be this. So forward force will be PA and backward will be P plus dPA. In this case, the downward along the x-axis acting force will be rho a dxz sin theta. Sin theta equals to actually ds by dx from figure. Okay, from figure we can write. We can use this method also for finding the Bernoulli's equation. So just integrating, we get this. Now, application of Bernoulli's. A pilot tube is fixed on the wing of an aeroplane to measure the speed of aeroplane. The tube contains liquid density 800 kg per meter cube, and the level of the two limbs is 0.5 meter. Density of air is given. Calculate the speed of aeroplane. So half rho b square equals to is dz. Just putting these values, we get the velocity of aeroplane. Now, a Venturimeter. A Venturimeter consists of a horizontal tube as shown in figure. It is different cross section at A and B. Okay, this is the actually Venturimeter. Here is the pressure P1 in A part and pressure P2 is B part. This is the size, small size, and this is the bigger size. That means volume bigger and volume smaller. So according to the Bernoulli's theorem, we get the total energy before equals to total energy after. If velocity B2 is greater than B1, therefore pressure P1 will be greater than P1 because pressure and force acting on opposite. The pressure difference at A and B is indicated by the manometer limbs. Now another application of Bernoulli principle. A horizontal tube has different areas of cross section at 2 points P1, P2. The diameter at P1 is 0.04 meter and the diameter at P2 is this. So two manometer limbs are fixed at P and Q when a liquid of density 800 kg per meter cube flows through. The difference in the pressure between the manometer limbs is this. Now calculate the rate of flow of the liquid through the tube. Now we get, according to the Bernoulli principle, energy before equals to energy after. This is the pressure P1 and this is the kinetic energy. This is the potential energy. So total energy before equals to total energy after. Now here H1 equals to H2 given height is same. This is why you can calculate BT equals to this. Now P1 minus PT equals to just putting the values we get. Calculate the speed at which the velocity of head of a stream of water is equal to the 0.50 meter of hg. Velocity of head will be b square by 2z meter water. This is the formula for velocity of head, and velocity of head can be written, can be found b equals to 11.54 meter per second. Now, another application of Bernoulli's equation. A railway engine is fitted with a tube whose one end is inside a reservoir of water in between the rails. The other is the tube 4 meter above the surface of the water in the reservoir. Calculate the speed of the which water rushes out the upper end if the engine is moving with the speed of 108 km per hour. This is the total energy before and this total energy after. It's just potential and kinetic energy. Pressure is absent here. So just alternating, B1 equals to this and H1 minus H2 equals to 4 meter. This is the given values. Similarly, this is another example for you. this left for you. This is also another example left for the reader. Same formula for the horizontal pipeline. This is another example of Bernoulli's principle or Bernoulli's equation. A Venturimeter has a pipe diameter of 0.2 meter through throat diameter 0.15 meter. The levels of water column in the two limbs differ by 0.1 meter. Calculate the amount of water discharged through the pipe in 1 hour. Density of water is 1000 kilogram per hour per meter cube. So rate of flow, this is the formula. Rho equals to given. So P1 minus P2 is given. So just putting the values. Similar example left for you. This is another application of Bernoulli principles. This is the Torricelli's theorem. Actually, this is the another advanced part of the Bernoulli's principle. So according to the Bernoulli's theorem, potential kinetic energy plus potential energy plus pressure equals to constant. So this is part A, and this is the height is1 from the O point, and this is the another height is2. Okay. This is the B point. So as P is the same at the free surface at the so B square by 2 plus Z is equals to constant. At A, B equals to 0, A is equals to S1. At A point, A is equals to S point, and velocity will be 0 steady. This is Y. So Z is 1 equals to B square by 2, or B equals to twice Z raised. The horizontal range L equals to BT, S equals to BT, distance equals to velocity multiply time. So L equals to B time root over 2S2 by Z. Just putting the values, we get the required. Now differentiating, this is differentiating with respect to L, and here we get dl by dA is 1 with respect to A is 1. For maximum L, first derivative will be 0. So first derivative equals to what? This 4 is minus 8 is 1 plus 0. Here is 1 equals to half capital is. Therefore, for the range of the liquid to be maximum, the or phase must be at the half of the height of the liquid of the column. Another example, a tank of containing water has an office on one vertical side. If the center of the office will be or fly switch 4.9 meter below the surface level in the tank. Just we have to find out the velocity of discharge. Actually, kinetic energy equals to potential energy. In that case, B equals to this. Just putting the values. This is very easy example for you. So actually, we have discussed here in Bernoulli equation and its application. So this is the Bernoulli's equation. We have proved as a fluid, and this given in 1738, Swiss physicist and mathematician Daniel Bernoulli derived the expression. So consequence of energy of conservation and applied to an ideal fluid. In deriving Bernoulli's equation, we again assume that the fluid incompressible fluid density is constant. Okay, consider the flow of the non-uniform pipe at the time del t. This is actually pipe or tube, and here pressure given F1 and a little change in length del L1 and velocity B1 here, and the height is 1. Here height will be H2. Okay, and pressure will be F2 for this surface. So the work done will be force F1 del L1. So F1 equals to rho 1 A1 del L1. So del B equals to A1 del L2. That means work done first for the first part will be P1 del B. Here del B is the volume of the lower blue region in the picture. It is similar to the manner the work done on the fluid of the upper portion. This is the upper portion. So W2 will be minus F2 because minus negative indicate the for the opposite force. So W2 equals to minus P2 del V. So the volume is the same because by the equation of continuity, the volume of the liquid that passes through S1 at the del T time equals the volume of the passes through the S2 part in the same interval. So the work done at 2 is negative because the force of the fluid on the top and opposite is displacement. The work done on the force at the time del T will be W equals to just difference. Total work done. Now total kinetic energy half m B2 minus B1 whole square, and the potential energy will be mg. H means was distance, difference between the distance. So total work done will be kinetic energy plus potential energy. So substitute the expression for each of the term, just putting the values here. Now if we divide each term by del B and rho equals to del m by del B, this is the space density. Density definition we have discussed in our previous slide. So per unit mass per unit volume is called density. So P1 minus P2 equals to this one. Just del B taking common. Now rearranging this part, P1 plus rho ZH1 plus half rho B1 square equals to, that means total energy before equals to total energy after. And this is the Bernoulli equation of an expressed as P plus rho ZH plus half rho B square equals to constant. So Bernoulli equation states that the sum of the external pressure P, this is the P is the external pressure, and hydrodynamic pressure, that means kinetic energy per unit volume. Kinetic energy per unit volume, half rho B square. And hydrostatic pressure. Hydrostatic pressure means the potential energy per unit volume. Okay, H rho Z has the same value at all points along the streamline or along the pipe or along the any tube. This is the main statement. This is the main statement for the Bernoulli's equation or Bernoulli's principle. And this is the Daniel Bernoulli, who is the founder of this equation. So an important consequence of Bernoulli equation can be demonstrated by considering picture. This is the picture we are discussing. So this is the total energy before and total energy after. So applied to points 1 and 2 gives, actually this is the constant. Application of Bernoulli's principle. Bernoulli's equation can be seen in various places around us. Here are some examples of Bernoulli's equation. This is actually train. A person who stands near a railway feels like falling into it when suddenly a train moves with a high speed passes him. It is because the velocity of air in front of him decreases. According to Bernoulli's principle, the pressure of the moving air decreases as the speed of the air increases. Okay, the higher atmospheric pressure behind pushed him forward. So this is the real life example for us to understand what is the Bernoulli's equation or Bernoulli's principle. So this is the shape of wing, and this the in this picture force air travel faster over the covered upper surface, and it does over the flatter lower surface. According to Bernoulli's equation, the pressure above the wing is lower faster moving air for the faster moving air, while the pressure below the wing is higher for the slower moving air. The wing is lifted upward due to the higher pressure on the bottom of the wing. This is the real life example of Bernoulli's equation. And this is the Torricelli's theorem we have discussed in our previous slide. And applying Bernoulli's equation, we can derive this one. So consequently, you can apply this Bernoulli's equation obtained on the assumption that for the pressure in both section at atmosphere, therefore the same P1, P2 equals to P naught. In addition, velocity of the open surface, the weight vessels in the assumed equal to 0. So in that case, with a view to everything, everything said have equation 1 can be written in the following way. Okay, and B is the velocity of the liquid flowing from the hole. Cancelling rho and introducing S equals to S1 minus S2, that means the height of the open surface of the liquid above the hole. We get B equals to S twice root over twice Gs. This formula is known as the Torricelli formula. Torricelli formula. So after the Italian physicist Evan Gaslista Torricelli gives this formula. This formula can be states that the velocity with which a liquid is discharged from a hole at a depth of S under an open surface coincides with the velocity which a body requires in falling from the height S. This is the actually height S from this point. This is the S2 height and S height. So total S1. So S equals to what? S2 minus S1. Here, here in the upper surface, velocity is 0, but here velocity equals to B. So this is another example. Pitot pipe. We can this example given by Henry Pitot in the 18th century. Flow of velocity and pressure in horizontal pipe can be measured using vertical pipes. So this is the actually vertical pipes. This is another pipe. So however, Bernoulli equation in horizontal pipe for the horizontal pipe, this horizontal pipe will be this. And B1, if B1 equals to 0 and B2 equals to B, we can be written B1 equals to this. So since the difference of in pressure, P1 minus P2 equals to rho Gs del S. So solving in flow of velocity, we get this B equals to root over. So fluid flow in Venturimeter. This also can be application of Venturimeter. Just using the continuity equation, Venturimeter is a device to measure the flow speed of incompressible fluid like water. The basic principle on which it works is that by reducing the cross-section area of the flow passes, the pressure difference is measured by using different U types tube manometer. This is the U types, okay? And here this is the actually pipe. This is the A1 portion, this is the A2 portion. This is the bigger diameter, this is the smaller diameter. Here velocity B1 and velocity here velocity 2. So this is the height S1. The speed B1 is the liquid flowing through the tube, the inlet area A1 to be measured from the equation of continuity will be this. So the speed of the at the throat becomes B2. B2 equals to B1 A1 divided by B2. Since the difference in pressure P1 minus P2 equals to rho 1 Gs, so using Bernoulli equation for the horizontal pipe will be this. So before energy equals to after energy. So P1 minus P2 equals to this. Now substitute the expression for each of the terms will be rho 1 Gs equals to this, because using equation number 2 here. Okay, here we get. Now solving for the speed B1 equals to this. It follows that the volume flow rate is equal to QB equals to A1 B1. This equals to this. Where the coefficient is determined experimentally, it is called the Venturi coefficient. Now we can solve some open problem for you. This is homework for you. So Bernoulli principle, we get Daniel Bernoulli found that the faster fluid moves, the less pressure it exerts. So Bernoulli principle means the pressure exerted by a moving fluid is less than the pressure of the surrounding fluid. Things move from area of high pressure to low pressure. This is the actually main, this is the application, how airplane flies, we have discussed in briefly here. And this is the application of Bernoulli's principle. This is another application, spoiler on a car and upside down wing. Okay, we have discussed this example. How many spray atomizer works like perfume bottle? Perfume bottle also works with the principle of Bernoulli. So this is the low pressure and high density. So squeeze valve and which makes the fluid move in top part, which lower the pressure. Fluid is in the bottom and it moves from its higher pressure area to top low pressure areas. So this is the actually Bernoulli principle. This is the different for the different liquids. This is the viscosity of selected gases. This is the standard values, and this is the fluid honey will be viscosity like this, and viscosity at 25 degrees centigrade. And viscosity of atmospheric materials. This is the temperature on x-axis, and this viscosity on y-axis. This is the references we have discussed. So thanks to everybody for being with us. So actually we have discussed the chapter fluid dynamics connecting with viscosity, these topics, and we especially have discussed the